see the new technique for input-output organization. So our current context is to discuss how the various input and output devices are connected for serving our or CPU request. These are the contents for our today's presentation. First we will going to discuss background, then we are going to discuss what is input output interface. The next topic is related to the data transfer, then the mode of transfer, DMA and the rest. Let us start with a background. So on the current slide you can see that we have one block diagram consists of three entities. First is a CPU, second is a IO interface and a third is a peripheral. So let us identify their roles and their responsibility. First, CPU. Now CPU is the central entity for executing the user's program. Now all the instructions will be executed inside the CPU. Now sometimes all these instructions that CPU is executing cannot be available or stored inside the CPU. Thus we need to read or write some programs from the CPU. Here comes our second entity from our block diagram, peripherals. So all the input output devices attached with the CPU are called peripheral devices. And the third one is a IO interface. Guys, you can see that it is a simple bridge between the CPU and a peripheral. Now there are certain questions in your mind. Why we require this bridge, this IO interface? Why can't a CPU communicate with a peripheral device directly? So the answer is over here in the next slide. Over here you can see that the peripheral and the CPU differences are enlisted. So very first thing is peripherals. Those are the input output devices can be recognized as a electromechanical or electromagnetic devices. And in front of that CPU is an electronic device, mostly a signal based performance device. Second point in the input output device is a very slow data transfer rate, as the way CPU is processing, the speed of the CPU can never match with the speed of the any input output device. You can take the example of the keyboard versus CPU. Keyboard is an input device, cannot perform at the same speed where the CPU is performing. Hence the peripheral devices works at the slower data rate while the CPU works on the faster data rate. Now the next point is peripheral device are the very small devices in the size, so they can have a capacity to transfer the data in the form of bytes or the codes or the bits, while the CPU is generally having the instruction format in a particular architecture, so it mostly prefers the word transfer format. Now peripheral devices are the electromechanical or electromagnetic devices. They can be operated with a various operating mode, while the CPU cannot be operated in any operating mode. So in this slide you can see that the devices that are the direct control of computer are connected with some set of the lines. Now the input output devices can be categorized into the three various types. Very first is input peripheral, that can be the light pen, mouse, a touch screen or a joystick. These are the input devices from where you can input something to the CPU. The other class of the peripheral device is output peripherals. These are the devices where some sort of output you can see, whether in the form of some audio or video. Let us take few examples. The control terminal, LCD display and a printer. One can put a speaker over here as well. The third category is the mixture of input output devices, that is input output peripheral. You can see the first example I have quoted is headphone, because headphone you can use for listening the audio as well as for receiving the command for as a microcontroller. Nowadays we have a Alexa skill device. These devices are the audio voice command enabled. So now when you command your Alexa device, it will generate some sort of output for you. So this device is a perfect example of a input output peripheral. Now these input output peripherals are having all set of devices, starting from the small mouse to the projectors to the terminals. So how they are communicating with a CPU? So here comes the role of an interface. Let us see what is an input output interface, shortly known as an IO interface. Okay, IO interface, as you can see in the presentation, it provides a method for transferring information between the memory and a CPU register to some IO devices. So now they all the peripheral devices require some sort of interface to communicate with a CPU, but a magnetic disk or a magnetic tape. Now whether it is a memory or any input output peripheral device, we require one interface to communicate with a CPU. Over here you can see there are three set of lines coming out of the processor. Very first is the IO bus that is connected with a interface. The second is the data bus and an address control. Now when I say that I want to deal with a memory, that means I require some sort of address on which I want to apply some read or write action. So we require address lines, and if you want to perform read operation for any IO peripheral or memory device, you require a data lines. So now if we think of one interface, you can see over here what can be there in an interface. So interface could be able to receive following things. Very first is the control, second is the status, third is the data output, and fourth is the data input. These are the four types of commands to communicate the data transfer between the processor to the peripherals, from peripherals to the processors, and through peripheral to memory to processor, vice versa. Over here you can see the complete description of all the commands I have discussed in the previous slide. Please go through it. They are simply as simple as you can read it up. Let's go ahead. Fine. Now over here we have a concept of IO bus and a memory bus. Now when you say a bus means, we have already discussed in the unit 2, a bus is a set of connection of wires. Now what is an IO bus? IO bus used to transfer or carry the data between IO device to the CPU through interface unit. Second entity is a memory bus. Now memory bus is used to transfer data between CPU and a memory. Now you have two entities, they are communicating with a CPU. What are they? Yes, one entity is a IO peripheral and a second entity is a memory. So how these three things are communicating with each other? There are possibly three ways to communicate with memory and IO from CPU perspective. The first way is, let us provide two separate set of bus for each unit, that is memory or IO. Second option is, let us provide common bus for data and separate control lines for each. This is necessary because the keyboard is having the different set of command control lines while the memory is having the different set of control lines. Let us go with a third one. In third case, you have a common bus for the data transfer and the common bus for the control lines. So in this diagram you can see the very first thing is a two separate bus for each unit. Now you can see the complete schematic of the system. There is one entity CPU communicating with two different entities, memory and IO device. You can see there are two individual buses available. One is a memory bus, second is a IO bus. Mind well, both the buses are bidirectional. It can carry information from CPU to memory, from memory to CPU, and the same case with a IO devices. What is the disadvantage over here? The disadvantage is you are having a common bus, but what about the control signals? That is the first question we need to ask. Second thing is, what if I have a single memory but n number of IO devices? My bus configuration will become very complex to handle. To overcome the limit of first technique, there is a second technique, common bus for data but separate bus for control lines. So the diagram speaks this up. The central unit is again a CPU. There are two entities communicating with a CPU. They are memory and IO devices. Now on the upper half of the diagram, you can see the common data bus for the memory and IO. That means if CPU wants to read or write something to the memory, the data will flow in this direction from the CPU to memory in the orange path, and the same with a IO device. But to apply the read or the write operation, CPU must apply the read or write signal. We can say it is activating a signal. So if CPU should activate read operation or a read signal, it will communicate via this blue path. The same is the case with a IO device. That's why we have a separate bus of control lines in this technique. In many literature it is known as a command lines as well. You can refer or interpret in any of the way you want. Now the third technique is common bus for data and common bus for the control line. Let us go with a limitation of the second technique. What is the limitation of the second technique? Again the same. If you have n number of IO devices, you may have n number of control lines, separate control lines for all of them. So it will again mash up all your configuration or fabrication. So let us go with a third technique where the common bus for data transfer concept is taken from the previous method, and they have clubbed up the control lines for the CPU, for the memory and the IO with CPU. Now what is the advantage? Programmer has to remember only the common control command, whether they want to read a memory or a IO. So this configuration is a hassle-free configuration. Let us discuss the pros and cons of all three techniques. So very first method, where we have a common bus for everything, what is the usage? It is used for the standalone PC having the separate IO processor and a separate memory. Well enough. Let's go with a second thing. In the second method, it suits for the system where you have a separate command and a limited IO devices with respect to limited commands. This is used for the specific application or application having the limited hardware. Let's go with a third technique. In the third method, for the system where they share the common command for each of the memory and the IO. This is a generalized or a uniform method for configuring the connection between CPU, memory and IO.